Hi. So, in today's class, we're going to talk about differentials. However, we already discussed differentials in length during our mathematics class. So, we're going to just grasp on what we've already learned because this is not very complicated. I just want to put your attention into a couple of things that are very crucial when we use differentials in economics and how we interpret those results. Okay, so let's start by going through definitions that we know. Okay, so we know that the derivative of some function y equals f of x, f prime of x, or equivalently stated is dy dx, and it's defined as a limit with delta x approaching 0 out of difference quotient delta y delta x. Okay, so this is the definition of the derivative that we've used many times. I hope you remember that this notation is the most appropriate when we talk about differentials. But let's start with something different. Look, let's go back for a second to our national income model. Look, in national income model, we were able to calculate equilibrium level of income, right? That was telling us what is the value of income in our economy given the values of exogenous variables. But this is not it. We also calculated comparative static derivative like this. Okay, what was this derivative equal to? Well, it depends on whether it was closed or open economy. In closed economy, it was 1 over 1 minus b times 1 minus t. How did we call this expression? This expression was called multiplier. Why did we call it multiplier? Well, it was telling us what's going to happen in this economy if we introduce some additional spending. So, let's imagine a situation like this. Our value of our multiplier in the economy is 3. Now, we know that government spending is increasing by 100. So, government decided to purchase goods and services worth $100 million, right? What will happen to GDP? Look, I didn't assume anything about what is the level of GDP initially, because this is actually not important in this model. Why? If I want to know by how much equilibrium GDP is going to increase, all I need to know is what is the value of the multiplier in our economy, and then I need to multiply it by the change in the level of government spending. So in our case, that would be 3 times 100 or 300. And look, of course, we would get that if government increases spending by 200, equilibrium GDP would rise by 600. And look, in this particular situation that we are dealing with, multiplier is constant, right? So, doesn't matter how much. What is the initial level of income, initial level of government spending? All I need to do is to multiply the multiplier by change in one of the autonomous values, so government spending, autonomous investment, or autonomous consumption, and I'm getting this result. Look, as everything in mathematics, this is not a coincidence. This comes from a very, very simple fact. This fact is that all the models that we have been considering thus far are linear models. Look, when you think about market model, Leontief model, national income model for open and closed economy, you never seen any squares, logarithms inside them. They were just very simple linear functions. Of course, example of a linear function could go like this. Y equals 2x plus 1. This is a linear function, right? However, y equals a plus b1 x1 plus b2 x2 plus bn xn is also a linear function. You know, the difference is that this is two-dimensional function, while this is n plus 1 dimensional functions, right? Because we have n variables on the right and one variable on the left. Okay, and look, when you are seeing consumption equal A plus B times disposable income, this is a linear function, right? Even if we add to it more, we still see linear functions, right? Look here, disposable income is simply defined as a difference between income and tax revenues. Again, this is a three-dimensional linear function. This is a two-dimensional linear function where tax revenues are equal to tax rate times income. And look, if I combine this here, what I'm still getting is a linear function, where this is a coefficient. And look, in cases where we have linear functions, so we do not have squares, we do not have logarithms, or anything else, have this property that their differentials, because their derivatives are constant, their differentials can be used more broadly than with general types of functions. Okay, let me explain this. Look, this is a function y equals 2x plus 1. Derivative of this function is just 2, right? Okay, let's go back to the definition of derivative, right? Derivative is dy dx, which is definitely equal to dy dx. But we remember that this identity, which nobody can argue is always true, can be easily transformed by multiplying both sides by dx. Of course, we are assuming that dx is different than 0. We're going to get out of this dy equals to dy dx times dx. Okay, what all those components are. Remember, this, as well as this, are differentials, right? So, what is this differential telling us? If x increases by some very, very small amount, dy, if x increases by some very small amount, y changes by this small amount times the value of the derivative. However, look, in case of a linear function, as it happens to be, derivative is constant, right? Derivative is always the same, which means that if x increases by 1 unit, y increases by 2 units. If x increases by 3 units, y increases by 6 units. And look, let's look on this example on a graph. Okay, so we've got a function. Let's just say we're going to start from 0, so the function continues over here, and it goes here. Okay, so let's just say we're starting at some, the simplest point. Let's just say that at 0. We see that over here, value of the function is simply 1, right? So now let's see what is going to happen to the value of the function if delta x, because we're not talking about the small number, is equal to 1. Okay, so we can clearly see that if delta x is equal to 1, it means that x increased from 0 to 1. So now x is 1, and the value of the function is equal to 3, right? So we get from this that when x increased by 1, y increased by 2, right? Makes perfect sense, right? Because here we have a situation, the derivative is constant, it really doesn't matter by how much I increase the value of x. I always know that value of y is going to increase by twice as much. Why? Because look, in our case, dy is equal to 2 times dx, right? Derivative is equal to 2, which means that every time when x changes by some amount, y changes by twice as much. And look, now, if x increases, let's just say from 1 to 6, which means that delta x is equal to 5. Then we can easily find the corresponding value of y, which is going to be 13, which is going to be 13. And we're going to see here the delta y is equal to 10, right? So if derivative is constant, which happens to be the case of linear functions, we can use trick like this, right? We can use the trick where if I want to predict by how much y is changing, all I need to do is to input change in y, and change in x, and I'm going to get resulting change in y. So look, in this case we've got the dy is equal to 2 times d delta x. Right? So in this case, we can actually use big deltas. It doesn't really matter how big is the change, the relationship between the two variables remains constant. Okay, and this is the relationship that we we're actually using while analyzing national income model. But as you can probably guess from what you already know, as well from what am I building with this, is that this characteristic of the linear functions is not shared with any other functions. And look, the easiest way to see it is, of course, to check it out on the example of another simple function. This time y equals x squared. Okay, look, if y equals x squared, then y prime is equal to x. And what is important in this relationship for us is that in this particular case, look, derivative is a function of x. Why is it so important? Because compare these situations. Every time when x was increasing by some amount, y was increasing by 2 times this amount in case of linear function, because here derivative was constant. However, over here, situation is different. Let's look at this one more time. If I'm going to write differential here, dy, it's still dy dx times dx. So dy, in our case, is equal to 2x dx. Okay, look, those two expressions are fundamentally different. Why? Look, because here, depending on what is the initial value of x, the value of the differential is going to be different. Again, let's see it on the graph. Okay, now I'm going to draw a parabola. So y equals x squared. Okay, and let's consider the case very similar as previously. So we start at 0. First, if x increases, so delta x is equal to 1. If x increases to 1, what happens? Well, y was 0. When I plug in here x equal to 1, I get that y is also equal to 1. So we see here that delta y is equal to 1. What happens then? If I'm going to increase x to 2, so again, delta x is equal to 1. What happens to the value of y? Well, if x is 2, y is 4, right? Which means that delta y over here is equal to 3. And then, if I'm going to move x a little bit more to the point 3, so delta x is still 1, we see that y is 9, or delta y is equal to 5. Okay, let's just do one more. And we see that if x is 4, so delta x is again 1. Okay, I'm starting to miss the curve, but we get that 16, and we see that delta y is equal to 7. So what is happening over here? Look, each time when x is taking a different value, the same increase in x actually results in bigger and bigger and bigger increase in y. Could we predict it somehow, knowing the different expression for differential? Of course. Look, the bigger, if x is 0, right? Then let's start with 1. If x is 1, then value of the derivative, right, f prime of 1 is 2. But then if value of x is 2, then f prime of 2 is 4. If it's 3, it's 6. So what we see over here, that is, the bigger is the value of x, the bigger is the sign of the derivative, is the value of the derivative. And consequently, change in y is going to be bigger. So look, what we cannot do in this case, and in case of any non-linear function, is to use the same trick that we did over here. I cannot tell you that if delta x is 3, then delta y is, let's just say, 16, unless I know what was x at the beginning, what was x at the end. So look, now, every time when we have non-linear function, we need to remember a very important thing. Derivatives are no longer constant, and we cannot use deltas. So, well, we still can use deltas, but we need to remember that we will not be able to use them to predict what is going to happen. Unless we take into consideration, of course, the change in the value of the derivative. But look, this creates a problem and an opportunity. Because look, when we actually calculated this derivative for function y equals x squared, what we found is the slope of this function. And look, slope of this function is definitely increasing, is getting steeper and steeper and steeper. And we see this from the derivative as well, right? The bigger the x, the bigger the 2x, so the bigger the first derivative, bigger the slope of the function. And look, actually, knowing the value of x, you can just substitute it here and get the slope of this function at any point. So, what we can do over here is to assess what is going to happen right around this point. But look, if we know how to do it for this point, we can do it for the next one, and for the next one, and for the next one, and for the next one. So, if we're going to be using differentials appropriately, we will be able to track what is going to happen, what is happening all over this curve. And look, again, this is important for economic reasons. Before we get to this, let me just get to a point. Let's just say that we have some non-linear model. And let's just say that this non-linear model implies that for some reason equilibrium is at this particular point. Right? We don't know why, we don't know the model. We know that it's non-linear and we know that the equilibrium is here. And look, using differentials, we can analyze what happens right around this equilibrium. Because look, when we talk about changes that do not throw off our economy completely into chaos, those are the changes that moves us away from our equilibrium, but usually somewhere in its close proximity. So we can actually just check what happens around this equilibrium, so we can expect what to happen. And look, if I calculate derivative at this equilibrium point, well, I see that it's downward sloping, right? So we can get from this that if we move to the right, we will be going down on y. If we move to the left, we'll be going up. So that is why actually using differentials is more powerful than using deltas. Well, deltas are very convenient for the easiest cases, where exposition just requires like extrapolation of some linearity, which just simply means that the same continues. However, the differentials are showing us what happens around a certain point, because we talk about very, very, very tiny distances, right? So, and because we can calculate differential at this point, and at any other point, we are able to see what is going to happen. And those smaller values, those dx's, are going to prove extremely important. Okay, but before I'm going to tell you the main reason why we use those, differentials, let's see case of non-linear function. Okay, another case of non-linear function. This time let's just say it's like some polynomial or something. Okay, so it looks like okay, again, what is the differential? Differential dy is equal to dy dx times dx, or dy equals to f prime of x times dx. I've written it in two forms because this is going to be the key to understanding what we get, what information we get out of the differential. Okay, look, imagine that we are at this point, at point where x is equal to x0 and y is equal to y0. Okay, so look, what do we get in this case? In this case, the differential, let's call it yellow differential, is given by f prime of x0 times dx. So what is this differential telling us? Well, it tells us that if x increases by some infinitely small amount, the value of y is going to go up. However, if x decreases, the value of y is going to go down. However, look, if we calculate a new derivative, new differential at point x1, so we will have dy equals f prime of x1 dx. What are we going to see? That if x is increasing, here we will have some y1, and if x is going to go up, because this is our derivative, then y is going to go down. However, if x is going to go down, y is going to go up. So I hope you can see that depending where we calculate the derivative, the value of the differential is going to be different, right? Which is a very important information. Now, what if we are at the top or at the bottom? Doesn't really matter. Look, here, value of the derivative is 0, right? So at x2, what do we see? That if x increases, like y2 increases. If x decreases, y also increases. And finally, if we are at the top over here and we calculate the derivative, we will see that if x increases, y goes down. If x decreases, y goes down as well. So, values of the differentials are going to tell us what is happening to the function as x changes around a certain point. But again, if we can calculate it for this point, for this point, and for this point, and for this point, we can calculate it for every point. And look, very often we are not interested by how much some variable is changing, but rather whether it's going to increase or decrease. Okay, and look, why is this? What is the magic of the differential? Differential allows us to calculate, to assess what happens over entire curve, right? And if we use this information appropriately, it's going to tell us how we should react to this change and what are the appropriate measures we should take into account in such a situation. Where do we need to have a knowledge in which exact point should we be? Well, obvious choice is to when we find maximum profit of a company. But this is what we've done already. So actually, we're going to use differentials for something that you've done in your microeconomics class, but we're going to look at it from a different perspective. We're going to do it more carefully and more meticulously, in the sense that we're going to be looking at every point. We're going to talk in the next video about elasticity. And elasticity is something that every company, in terms of elasticity of demand, wants to know where demand is elastic, inelastic, where it has point elasticity. And in those cases, differentials come to help us by quite a lot. Okay, so this is it about the introduction. In the next video, we're going to move to calculation of elasticities. Take care.